It's just nice. All right, so here is the study guide I wrote for you guys. So the first page is all about sequences. So I just kind of took a bunch of the notes and ideas and condensed them down. So this is meant to be like a quick reference guide when you're looking stuff up. So I definitely recommend you have this out. It's like yesterday, people would have it out on the table and they just weren't looking at it. I was like, guys, it's all right here. So I've got your properties, a lot of your algebraic stuff, right? Remember, for sequences, the only real test you have is the nth limit test. So, and a sequence can converge to any value, right? It's just what the list turns into. So remember when we were trying to take the nth limit, that's when we had a lot of different techniques. So we might have used the squeeze theorem, we might have used L'Hopital. Also, you guys have the added benefit this semester of literally all the lectures were recorded. So if you get stuck on something or you can't remember, you can actually go back and look at the class and see me do a bunch of examples and explain it. So that's a very good resource for you too. I also included on here about bounded and monotonic sequences. So remember, there's a lot of different ways you can justify whether something's converging or not. You don't always have to do algebra or algebra equations if you can justify your answer. If you have a sequence and it converges, you have to tell me the value it converges to. And the value is just the result of the limit. So it's not too bad, all right? Then I've got your commonly occurring limits. Remember, whenever you see these, you're allowed to just cite them right out. And don't forget that those X's stand for constants, right? So this is not like power series stuff. This is, you know, if you have X to the n, it could be like 1/2 to the n, right? Or if we've got this guy, this could be 1 + 2 over n, and we would know that's e squared. Also, make sure in your notes on this one, make sure you go back and you look. I gave you the format of what it looks like when we flip it upside down, right? Because when we flip it upside down, they tend to combine this into one fraction, so you need to make sure you know what 1/e to the x looks like. But those are two very, very useful limits. For series, right, we have our format of our series. We've got our partial sums. If we use partial sums to compute, we can just look at the limit. Then our algebraic properties of infinite series are in here. And then the second page is just the handout I gave you guys earlier, right? This was just kind of the logic chain you were supposed to look at when you're testing for convergence or divergence. And then on the back page, we have the table where I've numbered the rows that correspond to each of those bullet points on the first page. So you really need to keep this handy when you're looking at stuff. And if you look at it a lot while you're studying, it seeps into your brain. And I'm a very visual person, so like if I look at stuff like this, by the time the test runs, I'm literally able to picture segments of this. So, you know, so just seeing it written down is really, really helpful. And then the back page are power series stuff. So we've got, this is a power series centered at 0. Oh my God, I realized there's a typo here. I forgot my X's in this guy. That's not good. Can't believe I didn't catch that till just now. And then if it's centered at C, right, we have the X minus C term. So, can't believe I've been looking at this thing all semester and I didn't catch this. All right, so this should really look like a sub 0 plus a sub 1 times x plus a sub 2 times x squared. All right, that's what that should look like. Then I've got what your three possibilities for the radius of convergence could look like, right? Everything converges at its own center. So you could have a radius of 0, meaning only one value works, and that's the center for convergence. Or we could get a real number for r, like 1 or 2, and you can always check your interval because the center should be the middle of the interval. So always make sure, because I saw a lot of students working problems yesterday and they weren't thinking to like catch those ideas. So you won't know for sure if you're right or wrong, but you know that there are certain bullet points that have to agree with each other, and if you're kind of checking that along the way, you'll know that you're doing okay. If the limit works out to be, because remember we do this by taking the ratio test, if the limit works out to be 0, right? Well, 0 is less than 1. That means any value of x would work because you're going to get a 0 limit no matter what. So this is what an infinite radius would look like, and it's the whole number line. It means every value of x you plug in, it'll converge. Then down here, I put the algorithm that you use to generate a Taylor series from scratch. And down below, I put a table of really common series expanded out. And so the way you read this is they've expanded the series out, and then over here is the nth term. So if you sum the nth term, that's where you'll get the actual series. So we actually did this one right here in class yesterday, and we did it without doing the algorithm. We actually did it by turning it into a geometric series. So when you're doing practice problems, you can look at this, and if you recognize a series you can start with and manipulate, use it. And I told you guys on the test, I am going to give you a Taylor series question where I'm going to ask you to build the series, but you can build it from some other series that you can find. So make sure you look at the all the different ways we built series. So if you need the algorithm, you can use the algorithm, but if you recognize that it's like, let's say, a constant over a line, for example, you can just rework it and turn it into a geometric series, and you don't actually have to run through all the steps of taking the derivative. So that application stuff we did on Monday, make sure that you review that, but the video's online if you need to go back and watch how we did that. So I will give you a question where I ask you to build me a Taylor series that you can manipulate off of another series that you can build. And so pay attention to, are things derivatives of each other? Are they the integral of something else, right? Because we know we can integrate and differentiate Taylor series very quickly. All right, so that's the little study guide, quick reference guide. What do you guys have for me? So whatever y'all want to ask about, because I don't know what you don't know. Yep.
When you did the root test?
Yeah. I can't make these up on the fly, so I'm gonna look one up because things go really wrong when you try to make these up. All right, let's see. Here we go. All right, so the tell in a root test is when you have a bunch of stuff raised to the n, okay? So all right, so every single element of this series is raised to the n. So if you want to apply the root test, the first thing you want to do is you want to rewrite the series where you group all the stuff raised to the n together. So I can actually rewrite this as 6 over n plus 1 all raised to the n. And so the root test, like the ratio test, is a test for absolute convergence, so that means it's going to involve an absolute value. The root and ratio tests are really nice because that and the integral test are really the only ones where you get an actual definitive answer for convergence and divergence, right? The other ones are a little bit more subtle. So what we want to do on the root test is you want to take the nth root of the absolute value of a sub n. So we don't have any negative elements here, right? There's no -1 to the stuff. But if we did, when we take the absolute value, those would disappear anyway, okay? So if we take the nth root of this stuff, well, the nth root is the same thing as saying raising it to 1 over n. And so what it does is it wipes out the n. So you're just going to get this guy. Then you take the limit of your result as n goes to infinity. And the limit of this is clearly 0. So just like the ratio test, if the limit is less than 1, which this is, then it converges. If the result of the limit comes out to be something greater than 1, then it would diverge. If it's inconclusive, if it equals 1. All right, so I want to show you one more example which you can use the root test for. So this guy, right, it's not everything raised to the n, so it's kind of hard to regroup. So what I can do is this is kind of also kind of a manipulation of the geometric series. So I'm pretty sure this is going to diverge because we have a 5 on top and a 2 in the denominator. So that numerator is going to grow a lot faster than the denominator. So the nth limit of this is not going to be 0, right? It's definitely going to be something bigger than 1. So we can kind of see that it's going to diverge. So if you want to do this using the root test, what we could do is we could compare it to something that's all raised to the n. Okay, so if you want to say basically, well, I know this 1 is really insignificant, you could reasonably say that this is going to behave this way, right? Now, this is a form of the geometric series now, and we can clearly know that this guy's diverges, but we can do it using the root test. So just to show you another way of doing that. So once again, I'm going to write it as everything raised to the n. And when you take the nth root, I get 5/2, and clearly, right, the limit of a constant is just a constant. So that's greater than 1, and it diverges. Now, if I really wanted to do this in another way, I could say, well, if you want to prove something diverges by direct comparison, right, you have to find something smaller than that series that converges. And if you want to find something smaller, you need to make the denominator bigger. So I could also have done this using direct comparison by saying, well, 5 to the n over 2n plus 1 is greater than or equal to the series 5 to the n over 2 to the n plus 2 to the n. So I still am keeping it where the numerator is bigger than the denominator, so it's still got that same kind of form, but now what I've got something is that I can reduce and say, well, this is the series, right? And if you do 2 to the n plus 2 to the n, it's 2 times 2 to the n. It is not 4 to the n, okay? So this is really 5 over 2 to the n times 1/2. So this is also a geometric series where r is greater than 1. So I could use the geometric series and say, well, by the geometric series, this diverges. It's smaller than this, so this also diverges, right? Or I could apply the root test to this. Now, with the constant out front, the root test, you're going to get 1/2 over 1 to the n. And we actually know from our commonly occurring limits, if you wanted to do the limit of this, we know that any x raised to the 1 over n goes to 1. So if you applied the root test to this function, or this series, you would get 1/2 to the 1 over n times 5/2. So when you take the limit of this, oops, it's not to the 1/2, that's to the 1 over n. And that's just 1 times 5/2, which is still greater than 1. So you would still get that it diverges. So one of the things that's really kind of neat about this stuff is there are multiple ways that you can get to the answer, but all ways should lead you to the same conclusion if they're valid. So whatever way you see is good to do. But like I said, direct comparison is very, very tricky for some people because you have to compare the inequality in the right direction. And you also have to make sure that you haven't like violated the structure of the original series so you don't compare it to something like off the wall. All right. Cool. What else? Yep.
Could we work out a alternating series and find remainder and everything for it?
You're not going to need to do the remainder.
Okay.
Yeah, I told you guys in class I wanted to show it to you because if it comes up in other classes, but I'm not going to test you on the remainder. Because, but you need to be aware that the remainder exists because that is a good application. But when you come up with it in other classes, and what that remainder does is it helps you decide how many terms do you need to find. But when you do this in other courses, they will review the remainder theorem with you. You just don't want to see it cold turkey for the first time and somewhere else. But we don't really, I'm not really going to make you guys test you on that. There's just too many other things that are more important.
All right.
Yep.
Can you show how to use the ratio test to find R?
Yeah, so like find the interval of convergence?
Yeah.
Uh-huh.
Yeah.
Yep. Let's do one of those. So let me find an example. Oh, here we go. Love technology. All these problems at my fingertips. Okay. Let's see. Yeah, let's do something fun. If you do want to review the remainder stuff, I did do an example in class, and you guys also have the added benefit of, having your lectures recorded, so, oh no, wait, this isn't the one I wanted to do, sorry. It was this one. This one a little bit more fun, a little bit more algebra involved. Okay, so if we want to find the radius and interval of convergence, what you're supposed to do is you're supposed to perform the ratio test, okay? So the ratio test says find the absolute value of the n plus 1 term over the nth term. So one thing about notation here that people have been messing up, those absolute values immediately take away the -1 to the stuff, because -1, the absolute value of it is 1, and the absolute value of 1 is 1. So we can drop those. However, all the n values you're using are positive values, right? They're only going to be from 1 to infinity. But any x's that remain in the equations or any expressions with x, you have to keep the absolute value around that, because x could be any number on the number line. So you can't just drop the absolute values around your x's. So when we do this, the nth plus 1 term is going to be x minus 5 to the n plus 1 over n plus 1 to the 5n plus 1. And then when we divide, we multiply times the reciprocal of n 5 to the n over x minus 5 to the n. So this is what I want to simplify and then take the limit of. So this x minus 5 to the n is going to cancel the n here, and we're just going to be left with an x minus 5. The 5 to the n up top is going to cancel the n here, and we're just going to be left with a 5. So what I'm going to do when I write the limit is I'm going to kind of go ahead and group the like stuff together to make this a little easier to work with. So I'm going to have n over n plus 1. And then I'm going to have 1/5 in the denominator, and I still have the absolute value of x minus 5 in the numerator. So see, I was able to drop the absolute value around everything else because those are all positive, but I got to keep it around that x minus 5. So x minus 5 you treat like a constant, because in the limit, n is the variable. So the limit of the stuff in parentheses right here is just 1. Right? Everybody good with that? So what I end up getting is 1/5 times the absolute value of x minus 5. So in order to converge, the ratio test says, well, this stuff has to be less than 1. Okay? So the radius of convergence here is not 1, right? Because the radius of convergence, we need the form x minus c is less than r. So what I'll do here is I'll multiply both sides by 5. So my radius is in fact 5. And it's okay if you don't see it there. I always had trouble with that expression for some reason when I was first learning this stuff. But to find the interval of convergence, we need to solve this inequality. So we can drop the absolute value bars, and we can sandwich this expression between -5 and 5. And so then we solve for x, and we solve by adding 5 to both sides. So this is going to give me 0, x to 10. And I do recommend sketching it on a number line. And you can see here that the center is 5, because we can always visualize the center in these expressions. And the interval goes from 0 to 10. So you can also see here that the radius was 5, right? So the center should always be the middle of that interval. And so if you've done some algebra wrong, if that's not the case, because people were messing up solving for their inequalities. So you can see the radius is 5 there as well. So in order to find the actual interval of convergence, well, now I need to test these endpoints in the original series. So let's look at x equals 0. So when x equals 0, the series is -1 to the n plus 1. And when you plug 0 into x minus 5, you get -5 to the n over n times 5 to the n. So this -5 to the n over 5 to the n could really be written as -5 over 5 all raised to the n. Well, -5 over 5 is just -1. So I can take this out one step further because you want to simplify this as much as possible. And I get -1 to the n plus 1 times -1 to the n over n. Then, because I have the same base here, I can combine these -1s by adding the exponent. So when I do this together, I'm going to get -1 times, and it's not -1 times -1. You keep the base the same, but I'll get the sum of -1 to the 2n plus 1 over n. So that exponent is odd. 2n plus 1 are odd numbers. So that means this thing is going to alternate positive and negative. If I had gotten -1 to the 2n, then that would have simplified into +1, right? Because I would have just gotten even exponents, and -1 to an even exponent will always be 1. So what you've got here is the alternating harmonic series, and that converges. So that means it does converge at x equals 0. If we try x equals 10, well, then we're going to get n equals 0 to infinity. Oh, sorry, it's supposed to be 1. I don't know why I'm writing 0. -1 to the n plus 1. 10 minus 5 is +5 to the n over n 5 to the n. Well, now these guys cancel. And I get the alternating harmonic series again. So this also converges. So that means the interval of convergence is 0 to 10, and they're both included. So, right, we use parentheses when we don't include it. We use brackets when we do include it. So this thing is convergent at its endpoints. And when you do these, the series you get when you simplify it down should be something you recognize, and you should just be able to state convergence or divergence. So I don't need to see you run a bunch of more tests. When we're doing these types of problems, I'll let you just cite it, but you have to justify the convergence. So tell me it's an alternating harmonic series, tell me it's a harmonic series, a geometric series. You know, you can just state a P series, you can just state what you see and tell me if it converges or diverges. There's another section of the test where I just give you a bunch of series and I say, does it converge or diverge? That's where you have to run all the tests for me. So I'm trying to make sure that you guys aren't having to spin your wheels, because I want to make sure I hit all the topics and you have enough time to do everything. And there is an extra credit question on the test. You guys didn't take my exam 2, so you didn't know. But I always like on exam 2 and 3, I put an extra credit question on the test. It's just another topic, because I just understand in this material, even when you study and you know what you're doing, sometimes we always get hit with something and you just blank out because there's so much stuff. So the extra credit question is worth 10 points. So basically you can completely kind of ruin a problem, and you kind of have a chance to do like another problem in its place. It's just over a different thing that I just couldn't squeeze into the test. So I do that on my exam 2 and 3. So you have a chance to get 10 extra points on the test. Right? What else? Yep.
When you were solving for the interval of absolute value x minus c is less than r, why was r 1?
So r was not 1. Right? The 1 here is because that's what the ratio test needs for convergence. You have to make sure that whatever the x values you plug in here, it's less than 1. So then once you do that, that creates an expression for you. And for this particular problem, because we had a coefficient out here, I had to multiply by 5 to get it of that form. Because see, that form now matches this form. So this is where I can see the radius is 5. If you miss that, when you actually solve the whole inequality and draw the picture, you can literally visualize that the radius is in fact 5. And the center you should have been able to see, and then like I said, those things should match. That radius here should match the radius here, and otherwise you've made a mistake in your algebra if that's not happening. You've also made a mistake if the center is not in the middle of the interval. Yeah.
So, do you have to use the ratio test to find the?
Yes.
Okay.
Yep.
So that's how, if it says to do that, that's what you have to do?
Yep.
Okay.
Yep, that's how we do it, yep.
So the one that, where'd you get it from?
So that was right up here. So when we were simplifying, this 5 to the n only canceled the 5 to the n because this is really 5 to the n times 5.
But shouldn't it be, where did it, oh wait, no, sorry.
Okay.
So absolutely.
And so that's why I only struck out the n, because I was like, all right, so I'm still left with 5 to the 1. Yeah. Do you want to do another one of these? I can do another one if you want to see it done again, because I know this is a lot of steps. Okay. Yeah, let's do another one. I got plenty right here.
Could we find a power series representation and then like do the integral conversions of that? Like on the exam review?
What do you mean? Like, if you've got one, I can do the one from the review if you want to pull it up.
So is 1 over, or f of x equals 1 over 4 plus x squared?
Oh, yeah, that's a good one. Okay, yeah, this is a fun one. I was doing this in office hours. All right, so this is very similar to the one I did in class where we found arctan, okay? So if we wanted to find the power series of arctan, I was like, well, the derivative of arctan was 1 over 1 plus x squared, right? So we started with 1 over 1 plus x because that's a known power series, and then we manipulated it to turn it into that. So that's kind of what we're going to do here, all right? So if I want to, I have to do a little algebra on this guy to get it of the correct form. So if I want to use an existing power series, well, I need to turn this into a 1, okay? And the way that you do that is we factor the 4 out of the denominator. So when I factor the 4 out of the denominator, I now get this. So I'm going to write this as 1/4 times 1 over x squared over 2, or x squared over 4, okay? So what I'd like to do is, I know, I should really probably call this g of x so we don't get confused, right? I know that this is really easy to write the power series for because this is a geometric series, right? We said anytime we have a constant over a line, all we have to do is algebraically manipulate it and turn it into a geometric series. Furthermore, if I plug x squared over 4 into this equation, I'm going to get that right there. And that's what we did in class. So let's turn this into a series first, okay? So we want this to be geometric. We need it to be 1 minus our r value. So, right, we said we could write it like that, 1 minus x. So now we have a geometric series where our a is 1 and our r is negative x. So that means this should be the series from 0 to infinity of 1 times negative x to the n. So that's fine for a geometric series, but that's not really a power series. When you do a power series, the x expression should be x minus c to the n. There should be no coefficients. There should be no anything dividing by it. So what we can do is we can split this up, and I can say, well, that's really just negative 1 times x. So the power series, right, looks like that. So that's the series that I want to start with to turn it into my previous series. So now I'm just going to build f of x based on this. So the first thing I'm going to do is I'm going to plug x squared over 4 into my function. And we'll deal with the 1/4 in a minute because constants are easy. So we'll save that till the end. So if I want to now I've got, if I just plug x squared over 4 into this g of x function, I've now got this part of the function that I wanted to build. So that means just like, and this is something that I think a lot of people have been missing the boat on, these power series are just functions of x. They look really gross because of the sigma notation, but they're literally just f of x. So you can work with them algebraically in the same way you would work with any f of x function. So if all I had to do here was replace x with x squared over 4, all I have to do in the series is replace x with x squared over 4. So it's x squared over 4 raised to the n. But once again, I need to clean this up a little bit because we don't need all this stuff raised to the n, right? I need to like make it just some x term. So we're going to leave the negative 1 alone. And then I'm going to pull, this is 4 to the n on the bottom, right? Because it's being raised to the n. So I'm going to put this over 4 to the n. And now x squared to the n, right? You multiply the exponents, and I get x to the 2n. So now I've got this in the form of a power series. So I've got one more step to do to turn it back into f of x. So f of x, right, was 1/4 times this stuff. So since that's just a constant, we're allowed to move constants in and out of the series all day long. So that means I just multiply the stuff inside by 1/4. So 1 times negative 1 to the n is just itself, but 4 to the n times 4 gives me an extra 4. So this becomes 4 to the n plus 1, x to the 2n. So now I've got my Taylor series representation of my original function, right, 1 plus 4x squared. So is everybody okay with that? All right, so now you guys want to find the interval of convergence on this? Might as well, right? Let's just go nuts. Okay, so all you have to do is, it's so weird because I remember when I learned this stuff too, I wasn't getting it. It felt like magic. It just felt like we were hand waving stuff around. But it took me a while to like really realize, oh, these are just functions of x. You can work with them the same way, okay? So if we want to find the interval of convergence, that means we have to perform the ratio test on this guy. So the ratio test, right, says take the absolute value of the nth plus 1 term over the nth term. So that means the negative 1 of the stuff will go away. So I'll get x to the, and now this is where you gotta be careful. This is 2 times n, okay? So it's 2 times n plus 1 when you plug it in. It's not 2n plus 1, because then all you did there would have been multiplied by x. Over 4, when we plug in n plus 1 here, we'll get n plus 1 plus 1. So this is 4 to the n plus 2. Then we'll multiply times the reciprocal. So 4 to the n plus 1 goes up here, and x to the 2n goes down here. Now before I cancel, I want to write this out one more time, and I need to distribute this 2 across. So what I have now is x to the 2n plus 2 over x to the 2n times 4 to the n plus 1 over 4 to the n plus 2. So I just kind of regroup stuff. So now when I cancel things, this x to the 2n cancels the x to the 2n in the numerator, but I'm left with an x squared. And this 4 to the n plus 1 cancels 4 to the n plus 1, so I'm still left with 1/4. So what I need to take the limit of is the absolute value of x squared over 4. Technically, since x squared will always be positive, I can drop the absolute value and say, well, I just need to take the limit of this. So what's the limit of this going to be? It's just x squared over 4. There are no n's left, right? So the limit of a constant is just a constant. So now what I have is that x squared over 4 has to be less than 1. So that means x squared has to be less than 4. So this one's a little tricky because it's a quadratic and not a line, okay? So if I were to take the square root of both sides of this equation, right, I would get x could equal 2, like if it's a positive x, but it could also be negative 2, because negative 2 when you square it is also going to be 4. So if I'm looking at a number line, right, hopefully everybody's cool and can see that this guy was centered around 0, because we had an x minus 0. So that means the interval of convergence is values that are negative 2 to positive 2. Right? So now we need to check the endpoints. So if x is negative 2, and remember, we're plugging it into this series we found right here. Right, this was our final series we were finding the endpoints for. So when x is negative 2, I'll get negative 1 to the n. You have to put the negative 2 in parentheses and raise it to the 2n over 4 to the n plus 1. So in the same way that I got the 2n by saying it was x squared raised to the n, well, this is really negative 2 squared raised to the n. So that's actually going to become positive 4. So this guy simplifies quite nicely. We'll keep the negative 1 to the n, and really what I have is 4 to the n over 4 to the n plus 1. The 4 to the n's cancel, and I simply get the sum of negative 1 to the n over 4. So is this going to converge or diverge? Diverge. What's this going to look like? It's going to be 1/4, negative 1/4, positive 1/4, negative 1/4, positive 1/4, right? And we said when you have if you have the sum of a constant value, it will always diverge unless that value is 0. Okay? So we even did the simplest one we did was 1. If you have the sum of 1, you get 1, 2, 3, 4, 5, 6, right? You're just counting to infinity by 1. If you alternate 1, you get 1, negative 1, 1, negative 1, and we said that diverges because depending on where you stop or start, it will either sum to negative 1, 0, or 1. So there is no settling on the sum. So this thing will diverge, right? And it's going to fail. If you need a justification, right, it fails the nth limit test because the limit of this isn't going to exist. Okay? So now let's look at x equals positive 2. So if x equals positive 2, we get negative 1 to the n, positive 2 to the 2n over 4n plus 1. Well, that ends up simplifying to the exact same thing. So this also diverges. So the interval of convergence is negative 2 to 2 not included. So this one was had a little extra caveat because we had to build the series before we could start, but you perform the ratio test, set the result of the limit less than 1, solve for the interval, test the endpoints. And so these are really good problems to do for practice because you're doing a lot of intermediary steps, right? You're practicing the ratio test. More importantly, you're practicing all of your sigma algebra. And you're learning how to simplify things and all that stuff, yeah.
If one of them did converge, like, would it make sense to say it's less than 4 instead of less than equal to? How much that relates to?
No. It's always got to be strictly less because remember where that inequality comes from is the ratio test only converges when it is strictly less than 1. Remember, if it ever equaled 1, it's inconclusive. So your inequality that you create is a standard. You set the result of the limit less than 1 every single time. And the only time the radius will change is when you solve for that x minus c part of the expression. If you have to multiply by a constant or divide by a constant, right, that can happen too. So let's say the result of your limit was this. Let's say you did a problem and after you did the ratio test, right, the result of the limit let's say we did all the steps and the result of the limit was something like this. Okay? Well, just like before, you'd set it equal to or less than 1. And then when you solve this for x minus 2, see, now your radius would be 1/5 because you have to divide by a 5. So then 2 would be the center and you would get 2 plus 1/5 or negative 2 plus 1/5 when you solve for the interval of convergence. So you have to make sure that you're taking the limit and always starting with that expression less than 1. And all of your n's should be gone when the limit's over, because only x's should come out. All right, what else? Yep.
Can you just go over how to simplify factorials?
Yeah. So there was this really awesome problem that another teacher assigned, and I wish I could remember all the summation stuff, but the result, it was the result of the limit came down to simplifying a factorial. So what we ended up getting was this expression. So we did everything and we simplified, and we ended up getting this. Wait, sorry. It was n plus 2 factorial, right? So basically what happened was we did a bunch of algebra, and we got down to this expression, and we needed to simplify it down, okay? So if you ignore the x to the n for a minute, and we just deal with this stuff over here, well, the numerator factors into n plus 1 times n plus 2, okay? N plus 2 factorial says, well, multiply all the way up to n, so you have n factorial, but then to get to n plus 2, remember, you're never allowed to skip consecutive numbers when you're doing factorials. So this would say take n factorial, multiply it by n plus 1, and then multiply it by n plus 2. So then the n plus 1 and n plus 2 cancel, and this just simplified into 1 over n factorial times x to the n. So one of the things you want to be careful with is make sure that you recognize in factorials that this, right, is not equal to this, right? Here, the 2 is treated like a coefficient. You just calculate n factorial, then multiply the result by 2. Right? So this guy on the right is really read like this, right? But if I include the number in here, then you get, you have to go all the way to 2 to the n factorial. So if you want to simplify, let's say we have 2n factorial over 2n plus 2 factorial. So the numerator, you always want to leave the smaller factorial alone, okay? And what you want to do is you want to take the bigger factorial and you want to break it up in terms of the smaller factorial. So what this one is saying is go all the way up to 2 to the n, right? So multiply all those first 1 to 2 to the n. And then the next digit on the number line is 2n plus 1. And then the digit after that is 2n plus 2. So now the 2n factorials cancel and you end up with this. Right? So the big main idea in factorials is you're never allowed to skip a consecutive number. So there was a problem in web work where they gave them the series, and in the denominator it said 1 times 3 times 5 times 7, and everybody was doing the problem wrong because they were trying to write it as like 2n plus 1 factorial. Well, 2n plus 1 factorial, yeah, it goes up to an odd number, but it doesn't skip the even ones along the way. So if there's any consecutive numbers missing, you cannot write that as a factorial. And I actually did one like that on the quiz, and we weren't able to use a limit or anything else to figure it out. It was a sequence we were doing back in 9-1. And what you had to do was we actually used the fact that it was monotonic and decreasing to show that it converged, rather than trying to do a limit or something like that, because I couldn't put it in the terms of a factorial. I wasn't allowed to, because you can't skip digits. Does that make sense? Okay. All right. Anything else? Yep.
Do you have any advice of like algebra and trig stuff that we are going to need to know that might not?
Make sure you know the most common, like you do need to make sure you know the most common like derivatives. So like you need to know like the derivative of sine and cosine, you know. You need to know the derivative of arctan. Those are like the really famous ones. That's 1 over 1 plus x squared. But those are really the main ones that you want to make sure that you know. And I'm not really going to put too much trig stuff on here because you guys really didn't get to do Unit 2. But on my Unit 2 review video, one of the things we'll do is we'll go through how to do trig integrals, because you will need to know how to integrate trig functions in Calc 3, because in Calc 3 you use polar, spherical, and cylindrical coordinates, and those all involve sine, cosine, tangent. So one of the things that I want to make sure that we have is like a good rudimentary understanding of how do you work with trig integrals. So that'll be on that Chapter 8 video, and then we'll have, you know, some stuff on the final. Like I said, I'm not going to make it crushing. I'll try to stick to the most common stuff, but you'll always be able to revisit those videos back when you get into Calc 3 and you have to remember how do you work with trig integrals and stuff. And so one of the things that's really nice in Calc 3 is when you first see it, it seems bananas nuts, but like you will take a crazy expression in XYZ, because you're in 3 dimensions in Calc 3, and then by using polar or spherical coordinates, because of all the trig identities, you can collapse it down to something very simple. And it's actually easier to work with the trigonometry than it is to work with the rectangular coordinates. So yeah, but I won't do too much trig. But I would say you should know your derivatives and integrals of sine and cosine and arctan. Those are probably the 3 famous ones that come up, yeah.
Will we have so will we be doing 3D vectors for the final? Or?
Yes, we will spend, after the test, we will spend Monday of the following week. We'll do a day on vectors, and there will be a couple vector equations on the final. But we just barely stick our toe in the vector water, so it's very basic. And I really enjoy teaching the vector stuff because I'm going to teach it to you the way we would actually use it, like in physics or something, because I don't like the notation they do in math. But like if you guys ever see vectors again, I'll kind of try to do it in that format for you guys. But you will dot product, cross product, and that'll come up again in Calc 3. We're not going to go as far into vectors as some of the classes are, because the first week of Calc 3 they'll like review that stuff. Yeah.
So you're going to one class for the final?
We'll have the final, we'll have the test on Friday, and then we'll come back on Monday, and then Wednesday's reading day.
Tuesday we have Monday, Wednesday, Friday classes.
Oh, we do?
Yeah,
Yeah.
so we have Tuesday also for this
Like
class.
Tuesday we have the
Oh.
Friday, it's just Friday, it's not, I think it's just. the
Okay, so we have
Tuesday's
Monday and
Friday.
Tuesday. Okay, cool. Well, what we'll probably do then, oh, that means I'm short a day in my other class. I thought they were going to do the 2 days. All right, so what I was going to do in my other class, but we'll do that, is we'll do vectors. We have a little bit longer time, so we may be able to finish it, and what we might do is do a little bit more at the beginning of Tuesday, and then I'd like to spend the rest of Tuesday class just having another review day like this for the final, preferably so you guys can ask me like some Unit 1 and 2 stuff, so we can work some problems and talk through that. But you'll have those videos available to you as well.